Okay, so today we are going to see some application of whatever we have done so far in the area of reliability. Reliability is one of the very important area for engineer people because any product you talk about, it comes with warranty and all those stuff. And so reliability eventually talks about the lifetime study or life distribution study of the products, non-living products. And when we talk the similar thing for human being, then it becomes the survival analysis. And that survival analysis is applicable for your scheme of insurance, bank policies, other policies that is taken by the government for the entire population. So survival analysis and in general the demography. I think 2021 was the supposed to be the year of census for Indian population, but I don't know for this COVID situation whether it is on or not. Usually in 10 years gap they are doing the census. Anyway, let us talk about reliability. A few terminologies we will introduce and the necessary mathematics we will do. Rather, I should say application too. So whatever we have studied, we can see some bits and pieces which will be applied to reliability. So here, typically we start with this, that let t be a random variable, let t belongs to 0 to infinity, be a random variable representing the lifetime distribution of a product or component or system or machine, etc. For this purpose, we have also assume that T has continuous CDF, F and PDF, what you can get by the derivative F on 0 to infinity. 0 closed, 0 open, that doesn't matter too much, but for the time being it does. Now we define a term which is known as the hazard rate or failure rate. So we will talk about it. Suppose that the item has survived up to time t. Okay, first assume that suppose that an item has survived. That means a bulb is still on, or a machine is still working, a car is still working, something. In that sense, it is survived. I mean, the time before the first breakdown has survived up to time t. And we want to know the probability know the probability that it will not survive for an additional, just a second. So it will not survive for an additional dt or delta t time. Okay, so it has survived up to time t, and we are interested for the probability it will not survive for an additional dt time. So in this situation, how you can calculate the probability? You can calculate the probability as a conditional probability. Hence, probability t belongs to, say, t to t plus dt given t is greater than small t. So failure will occur in this small neighborhood when it is given that t has already crossed t. So as a consequence, already you have seen this kind of events when we have studied about the exponential distribution and geometric distribution. So probability t belongs to t to t plus delta t, or dt, divided by probability t, sorry, okay, so in this way t belongs to t to infinity, the same thing. So now this entire thing can be approximated with ft for this region, ft into dt whole divided by here 1 minus capital Ft. Okay, and this thing, if you want, you can also write in this way. Check whether it is okay or not. dds minus of log base e 1 minus fs, this derivative evaluated at s equals to t. Is it okay?
Sir,
So
what is
this,
fs here?
yeah, say again please.
Sir, what is fs here?
F is the CDF of this random variable. So you can write this thing as a dummy variable, I mean as a function. Then that function evaluate, the derivative of that function evaluated at time t. Is it okay?
So we have the dt, right? So we have to multiply this with dt to get the ft dt.
Oh, okay. Yes. Uh, yeah. Here we have to multiply with t. Here we have to multiply. So yeah, in this approximation, so here we use this notation lambda t, which is ft by 1 minus ft. So this is the density function, and this is 1 minus st is known as the survival function or the reliability function. We will write it. So this is also, you can write in general in this way, that ddt of minus log E 1 minus ft. So this quantity represents the conditional probability intensity, represents the conditional probability intensity that an item with age t will fail instantly. So this is known as hazard rate. Hazard rate or failure rate. This is the thing which is known as the hazard rate or failure rate. And okay, so let me write down in the other page. Lambda t equals to ft divided by 1 minus ft. This is hazard rate. And 1 minus ft is known as the survival function or reliability function. Or so it has the properties which is just opposite to the CDF. As t goes to infinity, it goes to 0. T goes to 0, it goes to 1. It is non-increasing function and all those stuff. It will hold for this survival function or reliability function. So quickly, can you please tell me what will be the hazard rate for if t follows exponential lambda, then what is the value of lambda t? The hazard rate. Quickly tell me. It is the easiest one. If t follows exponential distribution with rate lambda, then
So
what
lambda.
is the?
Lambda.
It is lambda, which is constant, and that is unique case. Hazard rate lambda only constant only for exponential distribution. Okay, another exercise I am leaving. It is very easy for you as homework. That show that 1 minus ft you can write as e to the power e to the power minus 0 to t lambda s ds, where lambda s is a hazard rate. Okay. So this is I am leaving as a homework. Just you will get from that identity that we have derived. Okay, now here this lambda, depending on this lambda t, you can characterize the probability distribution of a non-negative valued continuous random variable. So the distribution, it is an important fact that the distribution of a non-negative valued continuous random variable can be identified with its hazard rate. Okay. So if you know the hazard rate function, then definitely you will be able to get back the CDF. So for example, if lambda t is linear a plus bt, so t greater than 0, then ft equals to 1 minus e to the power minus at minus bt square by 2, and you can have small ft equals to a plus bt from here easily, e to the power minus at plus bt square by 2. Okay. When t greater than 0 and 0 otherwise. So as a special case, so this is just an example. You can not only have it is linear, it can have polynomial and many other forms also. It doesn't matter. So as a special case, if a equals to 0, then it represents Rayleigh distribution. Okay, so Rayleigh distribution is usually it comes from the chi-square distribution. So the square root of that. So you can have the form in this way, that f r, so let me write it down, sigma to the power minus 2 r e to the power minus r square by 2 sigma square when r greater than 0 and 0 otherwise. This is the PDF of Rayleigh distribution. The name is coming from this idea that suppose say x and y, they are IID, normal say 0 sigma square, then if you consider any pair xy, then you can plot them as a point, and x square plus y square follows sigma square times chi square 2 degrees of freedom, which we call r square, and the r, the square root of this quantity, which is said to follow Rayleigh distribution, because if you consider r, that is this length. If you consider another point x1 y1, that might be this one, another point x2 y2, that might be this. So in this is like, assume like this is a source of light and the rays are emerging from there. So this distribution is known as the Rayleigh distribution. So it is the square root of chi square 2 degrees of freedom distribution. So x square plus y square is follows sigma square. Sigma you can take 1, that doesn't matter. So this is chi square 2 degrees of freedom. Square root of that is r, positive square root, and that is said to follow Rayleigh distribution. And this is the interpretation why we call it a Rayleigh distribution. Eventually, this is the representative of the distance measure, Euclidean distance, more precisely. Okay, now we will see a little bit more interpretation of this rate. So say for example, if we consider this thing, that if we say for an adult person, that if we say that we say that the death rate of a smoker at each age is k times than that of a non-smoker. If we have this kind of statement, then what does it mean? Death rate of a smoker is at each age is k times than that of a non-smoker. So if we say, what will be the interpretation in terms of probability? So let us try to interpret it and try to check it from what will be the final conclusion. That both the person, so it means that both the person, then it means that if both the person are at age t and they have hazard rate lambda nt and lambda st for the non-smoker and the smoker respectively, then lambda st is k times lambda nt. This is the meaning. So if we talk about the rate of death, the rate of the failure or non death rate of smoker is k times of lambda nt. But what will be its meaning in terms of probability? So let us try to see that. Consider an a-year-old smoker will survive until B year, or maybe say age A will survive up to age B. So consider that an a-year-old non-smoker will survive until age B, where B is greater than A. Then if you consider this thing, that probability a-year-old non-smoker reaches age B, which means that non-smoker's lifetime is greater than B, given the lifetime is greater than A. Probability non-smoker's lifetime is greater than B, given non-smoker's lifetime is greater than A. So if you go by the probability, then 1 minus FB divided by 1 minus FA. Okay, and this thing you can write in this way from that homework that I have given. This is from my 0 to B lambda nt dt and 0 to a lambda nt dt, which is nothing but exponential minus a to b lambda nt dt. Similarly,
Hello, sir.
if we say the same event for smoker, then probability a year old smoker reaches age b is 1 minus you can use this expression directly, e to the power minus a to b, now it is lambda st dt. Now what you know, lambda st is k times lambda nt, so minus k times a to b lambda nt dt. Now what you can see easily that it is e to the power integration a to b lambda nt dt whole to the power k. So the probability here what you get is or probability here what you get is this power k, not divided or not multiplied by k or divided by k. So this probability is not 1/2, or say for if we set let k equals to 2, so the death rate of a smoker is twice than the non-smoker, if we say, then the probability of dying of a non-smoker is not twice the probability of dying of a probability of dying of a dying of a smoker. Oh, wait, what is it coming? Non-smoker probability of death is this, and the smoker's probability of death is this.
Sir,
Yes, wait, yeah, bolo.
sir, non-smoker lifetime greater than B means a-year-old man reaches till age B, so it should die after age B, no, sir?
Yes.
Its
So
lifetime should be less than B, no, sir?
oh, wait. Let me just check it.
No, sir, it is written survive until age B. So means at least be years old. He means at least till age B he must be alive.
So here I have written the death rate of a smoker at age is k times this. It means that the both of survived, they have hazarded this. So what I mean that whatever the smoker has survived up to age A, and I am interested to know whether they will this guy will survive even after age B.
That means it should be alive after B age also.
Yes, that is what I have written.
Okay, sir.
So they will start up to age A. They have this guy has survived, and I am interested for the conditional probability that that guy will survive still after age B. So that probability is coming as this. And so given t greater than A, I am interested for t greater than B. This is the event I am interested for, both of the person, smoker and non-smoker. Both of them have survived up to age A. I am interested to see whether smoker will survive even after age B, and non-smoker will also survive even after age B. So this probability for non-smoker is coming this, and for smoker is coming this. So this is a probability, and if you have k power and as a power, and if k is greater than 1, then this quantity is less than this quantity. Is it okay? Hello?
Yes, sir. It's okay.
Yes.
Yeah. So this quantity is less than this quantity, but it is not coming as half of this quantity. It is coming in the power. It is not becoming a scale multiplication. It is coming in the exponent. That is the difference we get, that might not be too clear from this English statement. From this English statement, only this much we can say, but in terms of probability, if we want to interpret, then this quantity is less than this quantity if k is greater than 1. So it is not 1/2 when k equals to 2, but this whatever, if I say, if this is as p square, not p by 2, it is p square. So this is just a special case if you put k equals to 2. When
Sir,
yeah, bolo.
sir, the formula which you have used in calculating 1 minus FB, that exponent e power minus, that is valid for all lambda, means as a function of t as well, or only for constant lambda means?
No. The lambda in general will be a function of t. Say for example this one. The exponential distribution is a special case when it is constant.
Okay, so the exercise 2 is for all types of lambda,
Yeah,
right?
exercise
The
2 is
function
for
of
general.
Okay.
This is for general. This is a special case, and it is unique characterization of exponential distribution. Hazard rate constant. Okay. Now, this is one aspect what people always deal with in reliability literature. Another thing that is also familiar to all of you, which is known the series and parallel circuits, or supply of different signals. So let us also interpret or see those kind of situation. So consider connection Okay, so here the input sources are coming, maybe like this. And so on and so forth. So Sk, S1, S2 up to Sk. So all these machines are in a parallel structure, and here you have a output, and so and the input sources are from here only. Okay, inputs. Now this machine will work, assume. So let so output system will work when at least one input system will work. Okay, at least one of them, if they are working, then this output system, whatever may it be the system, doesn't matter, it will work out of this K systems. Okay, so now if I'm interested to see that that let us first consider that the Ti is the lifetime distribution of Si, this source, and then what will be the lifetime distribution of this output system? Let X is the lifetime distribution of output system. What will be the lifetime distribution of this?
Max of Ti.
So max of Ti, right? Yeah. So if I say this thing that probability X less than equals to T, that means Ti less than equals to T for all I equals to 1, 2K. Is it okay?
Yes, sir.
Which also eventually this is true that max of Ti is less than equals to T. That is also true. The same thing. Now, and if we assume they are independent, then what it will be? Will it be this thing? Is it okay? Because of the independence. Each of Ti less than equals to T, they are product because they all are independent random variables. Okay. Now, what will be the reliability of the output system? Or reliability function? Of output system? What it should be? Reliability function is nothing but the 1 minus CDF or the survival function. So this is the CDF, right? So this is nothing but 1 minus fxt, which is 1 minus product over I running from 1 to k, probability xi less. Okay. Okay. So this is how it works for the parallel system. Now, if you go for a series system, so now if you consider series system, so similar way S1, S2, Sk. So from here the input, from here the output. Okay. Now again the same condition that Si has lifetime Ti and they are independent. And the output system has lifetime say again x, no problem. Then what is the probability that x less than equals to t?
So it should be like at least one of the system has x less than equals to t.
Okay, so you try to think in its complement.
1
Sir,
minus
1 minus minimum of Ti.
Yeah, so it is better to think that in the reverse direction, that this is one. So that means first of all minimum of maximum of Ti less than equals to t, right? Or wait,
The minimum.
minimum of Ti less than equals to t. I equals to 1 2 k. Yeah, that is the thing. So eventually, if you can see that it is 1 minus probability all Ti greater than t. Now again you can use the product 1 minus product over I running from 1 to k, probability of Ti greater than t. This is the thing. So survival 1 minus, so this is fxt equals to just the product of I running from 1 to k, probability of Ti greater than t. So this is for your series system, and this is for your parallel system. Okay, so this is in general true. Now we will see few examples when we will specify all these lifetime distributions and some interesting results we are going to see in this course. Page number 57. Okay, so let us try to see. So I hope you can understand why it is important to know the minimum of the distribution of the minimum of random variables, and as well as when it is important to know the distribution of the maximum of a collection of random variables. So let us first talk about this kind of thing, and gradually one after another special cases we will see. Okay. Tomorrow's class is there, so we can do lots of work there also. So let, in general, x1, x2, xn are IID with f continuous random variables. Okay. And you can have that f prime x equals to fx. That thing is given. Now define y equals to maximum of x1, x2, xn. So let us call gy is probability capital Y less than equals to small y. So can you please tell me what will be the expression of this quantity in terms of f, capital F? So usually this is denoted as x order n. This is known as the maximum order statistic. This is standard name in statistic literature. It is, and this notation is also standard. This is known as the maximum order statistics. So this is nothing but probability xn get less than equals to y. That means probability all of maximum is less than something. That means all are less than that quantity. x1 less than equals to y, x2 less than equals to y, and xk, or okay, I have written n here, so xn less than equals to y. And they are independent and identically distributed. So what will be the value of this quantity? Is it okay if I write
fy to the power n?
Yes. So this is fy to the power n. Very good. Now, given this, can you please quickly tell me what will be gy, the PDF of y? This is CDF. You know the formula now very well. You just tell me what will, from CDF to PDF, what will be the PDF?
Sir, fy to the power n log of fy.
In n into Bola?
N into capital Fy to the power n minus 1
Yes.
times
Then
small fn, small fy.
small f. Correct. So this is the PDF. Okay. Now, special case. Okay.
Sir,
Yes.
isn't n constant here?
Okay. For given date, given n is okay. So for the time being, that suppose you have n parallel system. Okay. Instead of k, you have n. So in that case, n is fixed. Is it okay?
Yes, sir.
So now special case. Okay. Case 1. Let xi's are IID uniform 01. They are IID uniform 01. Then can you please tell me what will be GY? Properly define the PDF. I have done this thing for general. Now I am just specifying a distribution Xi's are IID uniform 0, 1. Can you please tell me what will be the density function following this formula?
Nx power n minus 1 if x belongs to 0 to 1. And
Okay, so I am writing y, so I should write y here, right?
Yes.
N into y to the power n minus 1 when y belongs to 0 to 1, 0 otherwise. Can you identify the name of the distribution? Can you identify the name of the distribution? So try to at least think in this direction that how many distribution you have studied which are supported on 0, 1. You will be easily able to identify. Hello. What are the distributions you have studied which are supported on 0, 1? Apart from uniform 0, 1?
So Bernoulli and normal.
Normal doesn't support on 0, 1. Normal support on entire real line. I'm sorry. Bernoulli takes value only 0 and 1, not on the interval 0, 1. Continuous distribution. We are talking about continuous distribution. That means you are not studying. So can I also write here? Can I also?
Sir, gamma 1 comma lambda.
Gamma is supported from 0 to infinity.
So binomial.
Binomial is supported on the integer valued. See what are your conditions. All those things properly written in class, properly notes given, books are suggested. You are an IITian fellow.
Sir, beta n comma 1.
Yes, it is correct. It is beta n comma 1. So now it is very easy to identify its mean and variance. Expectation of y, variance of y. Homework. You know the formula for beta distribution, what will be the mean and variance. Get it from there. Okay, so tomorrow we will do the work for minimum. Okay, there you will see. So this is another connection from uniform to beta. Okay, and you will see more connections tomorrow from uniform to beta. So this is a connection between uniform to beta. Tomorrow you will see even more connections with uniform and beta. Okay, revise it very well, study it. Everything is at your hand. Even after that, if you cannot say this simple thing, it will be really problematic. Okay, thank you. See you tomorrow. And there is a sample question just to check your whether you can access the math symbols are loading or not. There were some issues with the math symbols in last exam. So before that, you try to check it, and if there is a problem, you try to sort it out, because there is no such issue we have found from our server here. If there is internet problem in your end, or maybe some add-ons or something is missing, you might face problem. If you can figure it out and sort it out, it will be nice. If it is still there, we are planning to have an alternative arrangement. Okay, so you check it and inform us if you have any difficulty. Okay, thank you. See you tomorrow.
Thank you, sir.
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 Yeah, bolo.